Right, so this is matter and radiation question 7. Explain what is meant by an isotope. So we've basically got the same proton number, it's the same element, but we've got a different neutron number. Nice and easy. Part B, okay, we've got a table here that's incomplete. So we've got two isotopes, 1 and 2. I'll try and draw this out. So we've got protons, number of protons, we've got neutrons, and we've got the specific charge of the nucleus. Right. Won't be that neat, but you should be able to see it. And we've got some numbers. We've got 92 for this first isotope. It's of uranium, so 92 says that in the question, I think. 143 neutrons, and then down here we've got a value for specific charge, 3.7 times 10 raised to the power 7. No units though, but I think that's the first question. Yes, it is. Writing the unit for the specific charge in the heading of the last column of the table. That should be always measured in coulombs per kilogram. Charge to mass ratio. Right, part 2. In the table above, write down the number of protons in the second isotope in the table. Well, isotopes just change the neutron number. They're not going to change the proton number, so that is going to be 92. It's going to be exactly the same. Part 3. Calculate the specific charge of the first isotope and write this in the table. So specific charge is Q over M. It's the ratio of the charge to mass. So the charges in this nucleus, and yeah, it doesn't say nucleus, but it really should do. Oh, it does say specific charge of the nucleus. It does say there. We've got 92 protons, so it's going to be 92 times the charge on a proton, which is 1.6 times 10 to the power minus 19. And we're going to divide all that by the mass of the entire nucleus, which is going to be 143 times 1.65 times 10 to the power minus 19. I think you have to take that as 1.66, not 19, sorry, minus 27. That's the mass. I'm thinking of charge. And really, for this one, we should include the mass of the electrons and stuff like that, but it does say nucleus, so I'm not going to bother. Plug that into your calculator, crunch it out, and we'll get 6.2 times 10 raised to the power 7 coulombs per kilogram. And that can just go in our table up here. 6.2 times 10 raised to the power 7. Specific charges generally do come out as quite big numbers because the mass is so small. So don't be put off by getting a big number like that. The next one, calculate the number of neutrons in the second isotope and put this number in the table. So we're kind of working backwards now. We've got the specific charge of the second isotope over here. We know the proton numbers, so let's write the number in here. Using the equation, specific charge is Q over M. Really, what I want to do is working out M, the mass of this nucleus. So I can rearrange that. Remember, we can just swap these two things about. So M is Q over specific charge. Right, so let's crunch those numbers out. What have we got? The charge is going to be 92 times 1.6 times 10 to the minus 19. That's the charge on a proton. And we're going to divide it now by the specific charge over here so that we can work out the mass over there. And we're given that 3.7 times 10 raised to the power 7. So that gives me a number. It'll give you about 978 times 10 raised to the power minus 25. That's in kilograms. I want the number of neutrons. So what I'm going to do is I'm going to divide this number by the average mass of a nucleon, 1.65 times 10 raised to the power minus 27. And that gives me an answer of about 241. It's actually 0.1 something or other. We can't have 0.1 of a neutron or anything like that, so that gives me 240. Now be careful, that is the nucleon number, not the neutrons. So to get the neutron number from that, I simply need to take away my 92. So 240 minus the proton number, 92, which gives me 149 neutrons. So I can put my answer in here, 149. That's it.